Hello everyone and welcome to our Class 10 journey. Today, we're diving into the fascinating world of chemical reactions and equations. Think about your daily life for a moment. Have you ever noticed what happens when you leave milk out at room temperature during a hot summer, or when an iron pan or nail is left out in the humid air? Perhaps you've seen grapes ferment, watched food being cooked, or thought about how our bodies digest what we eat and how we breathe through respiration. In every one of these situations, the original substance changes its nature and identity. When these chemical changes occur, we say a chemical reaction has taken place. You might be wondering, what exactly is a chemical reaction? And how can we tell one is happening? To find out, let's imagine ourselves in a laboratory. Our first experiment involves a magnesium ribbon about 3 to 4 centimeters long. Before we begin, we must clean it by rubbing it with sandpaper. Now, a quick word of caution. This activity requires a teacher's assistance, and it is highly recommended that you wear suitable eyeglasses for protection. As we hold the ribbon with tongs and burn it using a spirit lamp, we must keep it as far from our eyes as possible. You'll notice something spectacular. The magnesium ribbon burns with a dazzling white flame and transforms into a white powder. This powder is magnesium oxide, formed because the magnesium reacted with the oxygen in the air. But burning isn't the only way to see a reaction. Imagine taking lead nitrate solution and adding potassium iodide solution to it. You would see a yellow precipitate formation. In another setup, we could place a few zinc granules in a conical flask. If we carefully add dilute hydrochloric acid or sulfuric acid, and remember, always handle acids with extreme care, something happens around those zinc granules. You would see gas bubbles forming, and if you touch the flask, you'd feel it getting warmer. These experiments teach us that we can identify a chemical reaction by looking for 4 main signs: a change in state, a change in color, the evolution of a gas, or a change in temperature. As we look around us, we see a huge variety of these reactions, and we use symbolic representations to study them. Now, describing a reaction like magnesium ribbon burns in oxygen to become magnesium oxide is a bit long-winded. To make it simpler, we use chemical equations. The easiest starting point is a word equation. For our magnesium experiment, we write magnesium plus oxygen on the left side, then an arrow pointing to magnesium oxide on the right. The substances on the left are the reactants, the ones undergoing the change, and the new substance on the right is the product. That arrow in the middle doesn't just separate them. It shows the direction of the reaction. If there are multiple reactants or products, we simply link them with a plus sign. We can make this even more concise by using chemical formulae instead of words. Instead of writing out the names, we use symbols. Mg plus O2 reacts to form MgO. If you count the atoms on both sides, you might notice they aren't always equal. When the number of atoms of each element isn't the same on both sides, the mass isn't the same either, and we call this a skeletal chemical equation. It's just a basic outline of the reaction. However, science demands balance. Recall the law of conservation of mass from your earlier studies. Mass can neither be created nor destroyed in a chemical reaction. This means the total mass of the elements in the products must equal the total mass of the elements in the reactants. To satisfy this, the number of atoms for each element must remain the same before and after the reaction. Balancing an equation is a step-by-step process. For example, when zinc reacts with sulfuric acid to produce zinc sulfate and hydrogen, we can see by counting that the atoms of zinc, hydrogen, sulfur, and oxygen are already equal on both sides. That is a balanced equation. But what if they aren't balanced, like when iron reacts with steam to form iron oxide and hydrogen gas? We use what is referred to as the hit-and-trial method. First, we imagine boxes around each formula. We never change what is inside those boxes. We start by listing the atoms of each element on the left and right sides. It's often easiest to start with the compound that has the most atoms. In our iron example, we'd start with the oxygen atoms in the iron oxide. We'd put a coefficient of 4 in front of the water molecule on the left to match the 4 oxygen atoms on the right. Next, we'd look at the hydrogen atoms. Since we now have 8 on the left, we'd need to put a 4 in front of the hydrogen gas on the right. Finally, we'd balance the iron by putting a 3 in front of the iron atom on the left. After final check to ensure all atoms match, the equation is balanced. This is the hit-and-trial method because we use the smallest whole number coefficients to find the balance. To make these equations even more informative, we add symbols for physical states. S for solid, L for liquid, G for gas, and AQ for aqueous, which means the substance is dissolved in water. Sometimes we even use G for water to show it's being used as steam. We usually only include these if they are necessary for clarity. You might also see numbers or symbols above or below the reaction arrow. These indicate specific conditions like temperature, pressure, or a catalyst. For instance, the equation for photosynthesis includes sunlight and chlorophyll over the arrow to show what drives the reaction that creates glucose. As we move into the different types of reactions, remember that atoms don't just vanish or turn into other elements. Instead, chemical reactions involve breaking and making bonds between atoms to create new substances. The first type is a combination reaction. Imagine adding water slowly to calcium oxide, also known as quicklime, in a beaker. If you touch the beaker, you'll feel it getting very hot because the two substances react vigorously to form slaked lime or calcium hydroxide while releasing a lot of heat. Because these two reactants combine to form a single product, we call it a combination reaction. Interestingly, the slaked lime is used for whitewashing walls. Over 2 or 3 days, it reacts with carbon dioxide in the air to form a thin, shiny layer of calcium carbonate, which, by the way, has the same chemical formula as marble. In certain combination reaction, heat energy is released along with the products. Such reactions are called exothermic chemical reactions. Other examples include burning coal, the formation of water from hydrogen and oxygen, or burning natural gas. Even our own respiration is an exothermic process. We eat food like rice or bread, which contains carbohydrates that break down into glucose. This glucose reacts with oxygen in our cells to provide the energy we need to stay alive. Even the decomposition of vegetable matter into compost is exothermic. The opposite of a combination reaction is a decomposition reaction, where a single reactant breaks down into simpler products. In lab, heat green ferrous sulfate crystals. As they lose water and change color, they decompose into ferric oxide, sulfur dioxide, and sulfur trioxide. The pungent smell, the characteristic odor of burning sulfur is hard to ignore. What you are observing here is a single reactant breaking down into simpler products. Another example is heating limestone or calcium carbonate to produce carbon dioxide and quicklime, which is vital for making cement. When we use heat for this, it's called thermal decomposition. You can also see this when heating lead nitrate, which releases distinct brown fumes of nitrogen dioxide. Decomposition can also happen via electricity or light. In the electrolysis of water, an electric current breaks water down into hydrogen and oxygen gases. If you perform this, you'll notice the volume of gas in one test tube is double the other, because water has 2 parts of hydrogen for every 1 part of oxygen. Then there's photolysis, or decomposition by light. White silver chloride or silver bromide turns gray in sunlight because the light breaks the compound into silver metal and chlorine or bromine gas. These specific reactions were once the basis for black and white photography. Because all these decomposition reactions require energy, whether heat, light, or electricity, to break bonds, they are known as endothermic reactions. You can feel this if you mix barium hydroxide and ammonium chloride. The bottom of the conical glass will feel cold because energy is being absorbed. Now, let's look at what happens when elements compete. If you dip clean iron nails into a blue solution of copper sulfate, after about 20 minutes, the nails become brownish and the blue color of the solution fades. This is a displacement reaction. The iron is more reactive than copper, so it literally kicks the copper out of the solution and takes its place, forming iron sulfate. Zinc and lead can do the same thing to copper because they are also more reactive. In some reactions, the reactants just swap partners. This is a double displacement reaction. For example, if you mix sodium sulfate and barium chloride solutions, a white, insoluble substance forms immediately. We call this insoluble substance a precipitate, and the process is a precipitation reaction. This happens because there is an exchange of ions, specifically the barium ions and sulfate ions react to form the precipitate, while the sodium chloride stays in the solution. Our final major category is oxidation and reduction. If you heat copper powder in a dish, it becomes coated with black copper oxide because it gained oxygen. We say the copper has been oxidized. However, if you pass hydrogen gas over that heated black material, it turns brown again as it loses oxygen to become copper metal once more. In this case, the copper oxide is reduced. When one substance is oxidized and another is reduced in the same reaction, we call it a redox reaction. We can define oxidation as the gain of oxygen or loss of hydrogen, while reduction is the loss of oxygen or gain of hydrogen. You see this in many places, like when carbon is used to reduce zinc oxide into zinc. These oxidation reactions are all around us. Corrosion is a common example. Iron articles are shiny when new but develop a reddish-brown powder, rust, over time when exposed to moisture and air. Other metals corrode too, like the black coating on silver or the green coating on copper. Corrosion is a serious problem because it damages car bodies, bridges, ships, and railings, costing huge amounts of money every year. Then there is rancidity. Have you ever smelled old oil or fat? When fats and oils are oxidized, they become rancid and their taste and smell change. To prevent this, manufacturers add antioxidants or flush bags of chips with nitrogen gas to keep them fresh and prevent oxidation. To wrap everything up, let's summarize what we've learned today. A complete chemical equation is a symbolic way to represent reactants, products, and their physical states. We must always balance these equations so that the number of atoms of each type is the same on both sides, following the law of conservation of mass. We explored combination reactions where substances join together and decomposition reactions where they break apart. We learned that exothermic reactions release energy while endothermic reactions absorb it. We saw how more reactive elements displace others, how ions exchange in double displacement reactions, and how precipitation creates insoluble salts. Finally, we understood oxidation and reduction as the gain or loss of oxygen and hydrogen. Understanding these processes helps us see the chemistry in everything from a rusting bridge to the very air we breathe. With this, we have come to the end of this chapter. If you feel the video helped you in understanding the lesson better, please subscribe to the channel and share the channel link with your classmates. Take care and see you soon in the next video.